Hello, everybody. Today I'm going to provide an introduction to diffusion models, a family of models that have recently shown tremendous promise in the image generation space. While many approaches have been implemented for image generation, some of the more promising ones over time have been model families, like variational autoencoders, which encode images to a compressed size, then decode them back to the original size while learning the distribution of the data itself. GANs, which pit two neural networks against each other. One neural network, the generator, creates images, and the other neural network, the discriminator, predicts if the image is real or fake. Over time, the discriminator gets better at distinguishing between real and fake, and the generator gets better at creating real-looking fakes. Autoregressive models, which generate images by treating an image as a sequence of pixels. The modern approach with autoregressive models actually draws much of its inspiration from how LLMs handle text. One of the newer image generation model families, and the focus of this talk, is diffusion models. Diffusion models draw inspiration from physics, specifically thermodynamics, and while they were first introduced for image generation in 2015. It took a few years for the idea to really take off. Within the last few years, though, we've seen a massive increase in the research space and industry with diffusion models. Diffusion models underpin many state-of-the-art image generation models that you may be familiar with today. Diffusion models show promise across a number of different use cases. Unconditioned diffusion models, in which models have no additional input or instruction, can be trained on images of a specific thing to generate new images of that thing, such as faces. Another example of unconditioned generation is super resolution, increasing image quality. Conditioned diffusion models give us things like text to image, generating an image from a text prompt, and image editing or customizing an image with a text prompt. Let's dive into diffusion models and talk at a high level about how they actually work. In this talk, for simplicity, let's focus on unconditioned diffusion. Now, this is a really interesting idea. It's quite different than any other image generation approaches. Destroy structure in a data distribution through an iterative forward diffusion process. Learn a reverse diffusion process that restores structure in data. The goal is that by training a model to denoise, that model will be able to take in pure noise, and from it, synthesize a novel image. Now, I know there's a bit of math notation on this slide, so let's break it down a bit. We start a large dataset of images. Let's take a single image, shown here on the left. We start the forward diffusion process to go from x0, the initial image, to x1, the initial image, with a bit of noise. We can do this over and over again, iteratively, to add more and more noise to the image. This distribution we call Q, and it only depends on the previous step. We can do this over and over, iteratively adding more noise. Ideally, once we do this for a high enough T, we have reached a state of pure noise. The initial research paper implemented this with T Bors 1000. Now we want to do this in reverse. How do we go from xt noisy image to xt-1 slightly less noisy image? At each step of the way, we also learn this reverse diffusion process. That is, we train a machine learning model that takes in as input the noisy image and predicts the noise. Let's take a look at this from another angle. We can visualize a training step of this model. We have our initial image x, and we sample at time step t to create a noisy image. We train a denoising model to predict the noise. This model is trained to minimize the difference between the predicted noise and the actual noise added to the image. In other words, this model is able to remove noise from real images. To generate an image, we can start with pure noise and send it through our denoising model. We can then take the predicted noise and subtract it from the initial noise. If we do this iteratively, over and over, we end up with a generated image. Another way to think about this is that the model is able to learn the real data distribution of images it has seen and sample from that learned distribution to create new novel images. As I'm sure we are all aware, there have been many advancements in this space in just the last few years. While many of the exciting new technologies on Vertex AI for image generation are underpinned with diffusion models, lots of work has been done to generate images faster and with more control. We have also seen wonderful results combining the power of diffusion models with the power of LLMs for incredible, context-aware, photorealistic image generation. One great example of this is Imagen from Google Research. While it's a bit more complicated than what we've talked through in this session, you can see at its core, it's a composition of a LLM and a few diffusion-based models. This is a really exciting space, and I'm thrilled to see this wonderful technology make its way into enterprise-grade products on Vertex AI. Thank you for watching. Please feel free to check out our other videos for more topics like this one.